Moino, the leading name in progressing cavity equipment, pioneered and advanced the application of PC artificial lift at the encouragement of oil producers throughout the world. These successful producers have profited from the advantages that are unique to the Moino progressing cavity pump. Moino has over 50 years of experience in the most difficult and aggressive applications in industrial, municipal, and energy-related applications. From food, chemical, paper, and sewage, to coal, nuclear, and petroleum, Moino's broad application experience has resulted in volumes of successful case histories. Moino Engineering has developed a wide range of extremely specialized progressing cavity elements to meet petroleum exploration and production application needs. Directional drilling, saltwater or polymer injection, drilling mud transfer, tar sands, even shallow well artificial lift. Although we formally recognize 1981 as the year we introduced the Moino downhole pump, we have actually been supplying componentry and engineering consultation to the application since 1960. Moino progressing cavity pumps have been used as crude oil transfer pumps since 1940. Let's take an excerpt from the basic Moino introductory training program to set the stage for an examination of the specific technical features of the Moino downhole pump and how they benefit petroleum producers.
The progressing cavity pump was invented in 1929 by René Moignot, a French scientist and airplane design engineer. The pump was introduced commercially in the United States by Robinson Myers in 1936. Since then, it has been continually enhanced to meet the specific demands of many industries. The progressing cavity pump principle is deceptively simple. It consists of a moving element, normally a single helical rotor, and a stationary element, the double-threaded helical stator. The Moignot principle consists of a family of pumps where the stator always has one more helical thread than the rotor. The ratio of one rotor thread to two stator threads is the most common. When the rotor is placed inside the stator, a series of sealed cavities are formed, 180 degrees apart. As the rotor turns eccentrically inside the stator, the cavities progress from the suction port to the discharge port. As one cavity diminishes, the opposing cavity increases at exactly the same rate. Because there are no valves, the result is a low-velocity, non-pulsating positive displacement flow. Is the progressing cavity pump wizardry or calculated engineering? The basic design seems simple, but it takes complex engineering calculations to design a pump based on the progressing cavity principle. The capacity of a progressing cavity pump is determined by the size of the cavities formed between the rotor and the stator. The cavity size is affected by three factors: the cross-sectional diameter of the rotor, its eccentricity, and pitch length. The diameter and eccentricity of these two rotors are the same, but the pitch, the distance between one crest of the helix to the next, is different. The result is a difference in capacity proportional to the difference in pitch length. A progressing cavity pump's actual flow rate is also affected by the number of repeated seal lines. Seal lines are created wherever the rotor comes in contact with the stator. A complete set of seal lines forms what is called a stage, giving progressing cavity pumps their ability to overcome pressure in a system. When stages are added to the pumping element, pressure capability increases. A three-stage pump is able to hold capacity at 3 times the pressure of a one-stage pump. The material being pumped also influences the number of stages needed. Abrasives require more stages to extend pump life. The amount of internal leakage within any pump is called slip. The amount of slippage in a progressing cavity pump is related to the pressure and the viscosity of the fluid. Viscosity is the property of a fluid to resist flow. In a progressing cavity pump, The higher the viscosity of the fluid, the less slip will occur. Note the difference in slip between the low and high viscosity fluids at 120 psi. The potential for slip is greater when the pressure is higher. Note the slip, the difference in capacity, at 60 and 120 psi. In this example of a one-stage pump running at 300 RPM and handling a pressure of 40 psi, flow is 10 gallons per minute. At the same RPM, if system pressure is increased to 80 psi, flow decreases to 6 gallons per minute. The increase in system pressure from 40 to 80 psi results in an additional slip of 4 GPM. There are two ways to compensate for this slip. One is by increasing the RPM. The single-stage performance curve indicates that the pump must operate at 400 RPM to realize a flow of 10 GPM at 80 psi. The second alternative is to add another stage to the pump. This time, we refer to a two-stage performance curve. The two-stage pump can operate at 300 RPM and still realize a flow of 10 GPM at 80 psi.
And what does this mean to today's oil producer? It means a list of benefits, many obvious, some subtle, that all in one way or another represent improved profitability through a reduction in overall costs when compared to the typical costs of more traditional artificial lift techniques. A convenient place to start is also, in most cases, one of the first considerations of every producer planning a new well: the cost of production equipment. The tremendous reduction in size and complexity of the surface equipment usually represents the single biggest savings, as much as $40,000 in the higher capacity models. Even in the lower capacity sizes, the savings on surface equipment and installation costs typically more than offset the fact that the rotor and stator are more costly to manufacture than the standard rod pump they replace. When comparing the complete PC system versus a complete conventional system, producers the world over are first drawn to Moino as a means of reducing the cost of equipping this. Moino's small surface equipment size further saves effort and cost in transportation, safety and security enclosures, site preparation, and actual installation. The profile is inherently low enough that it does not interfere with overhead irrigation systems. And where surface equipment must be below grade or enclosed, the excavation or construction costs are minimized with Moino. In addition to reducing installation costs, Moino downhole oil well pumps will reduce your operating costs over the life of the equipment and therefore increase profitability. The rotary positive displacement performance of the progressing cavity pump is virtually always more efficient than either the pump jack and rod pump or the electric submersible centrifugal when they are operating at the same depth and capacity. The savings in energy costs to produce the same amount of petroleum mount up rapidly when you consider a PC pump is often 50% more efficient than a pump jack system and 200% more efficient than an electric submersible centrifugal pump. Moino users report savings to 65% in the cost of energy per barrel of oil produced. In electrified fields, the use of Moino downhole pumps can reduce the capital costs of power transmission lines. For an industry plagued by lightning, one of the more subtle savings might be in the reduction of risk exposure associated with a more efficient Moino pump that generally requires a smaller electric motor. This efficiency, inherent to the PC principle, has been further enhanced by Moino oilfield products through engineering design and high manufacturing standards. And the rotor and stator are manufactured to extremely close tolerances to assure the most consistent compression fit over the entire length of the parts, a fit that significantly reduces slip or volumetric inefficiency, resulting in an almost flat family of curves. At the same time, the compression is controlled to prevent unnecessary mechanical inefficiency. With reported run times up to 3 years between servicing, properly applied Moino downhole pumps are saving producers maintenance and workover costs. The progressing cavities metal rotor and elastomeric stator stand up under the widest range of abrasive formation fluids. Better than metal-to-metal pumps, especially high-speed centrifugals. Moino's positive displacement pumping action without any dependency on valves makes it unnatural for the gas-producing wells, eliminating downtime and workovers due to gas-locked pumps. The rotor turns on standard sucker rods, with the stator suspended on the tubing string. The Moino pump uses a simple rotary motion that eliminates rod drop problems common to heavy oil and tar sands, facilitates pump speed changes to adjust the production rate, and contributes to the mechanical efficiency by eliminating the need to lift rod along with the fluid. The versatile yet compact drive head is almost operator maintenance free. With only a few grease fittings and a packing box, conscientious operators are often inclined to provide more attention than is actually required. Since capacity is approximately proportional to speed, a change in the pump production rate is usually very easily and inexpensively accomplished by merely changing the belts and pulleys. For even easier speed changes, the Moino drive head allows the system to be supplied with your choice of variable speed devices, mechanical, hydraulic, or electrical. Where necessary, the Moino downhole pump can be driven by a gas engine. The Moino progressing cavity pump in an artificial lift application is less costly to purchase, extremely efficient, easy to maintain, inexpensive to operate, durable even in sandy application, very dependable, inherently safe, and very versatile within its expanding application range. Having vastly superior hydraulic characteristics compared to other conventional artificial lift principles, the progressing cavity pump is limited only by size and materials of construction. Moino continues to develop product line extensions as the industry's adoption of the product accelerates. The application engineers at Moino are unequaled in selection and installation experience with the PC downhole pump. Their services and database are available to our service distributors and their customers. Moino Oilfield Products, a unit of Robbins & Myers Incorporated, designs and manufactures progressing cavity components and accessories for subsurface applications, primarily petroleum exploration and production. The unit maintains operations in Tulsa, Oklahoma and Fairfield, California, with division manufacturing and technical support in Springfield, Ohio and Brantford, Ontario. Moino's research and manufacturing facilities and equipment are the most modern of all PC manufacturers in the world. Robbins & Myers is unsurpassed in its commitment and contribution to the diversification of the progressing cavity principle.
Moino downhole progressing cavity pump is designed, manufactured, and marketed by Robbins & Myers, a large, multifaceted company with a worldwide reputation for quality and service. Robbins & Myers Fluids Handling Group introduced the unique Moino progressing cavity pump to North America in 1936. Since then, the pump has been widely copied, but no company has more manufacturing experience and engineering know-how than Robbins & Myers. Over the years, Moino progressing cavity pumps have proven themselves again and again, pumping some of the toughest fluids in a wide range of applications. A Moino pump can handle virtually anything you can push through a pipe, from corrosive chemicals and heavy abrasive slurries to glue, grout, and even licorice candy. Moino has been serving the oil industry with efficient, dependable, progressing cavity surface transfer pumps for over 45 years. The progressing cavity design has also proven its value to the oil industry by providing superior downhole service in both production and drilling applications. Robbins & Myers designs and manufactures progressing cavity elements for mud motors used in drilling. Simple design, rugged construction, and low operating speeds enable the Moino downhole progressing cavity pump to meet the challenges of continuous downhole operation. The pumps have only one moving part downhole. There are no valves to stick, clog, or wear out. A Moino downhole pump won't gas lock. It treats gases just like other materials and pumps them out. It can easily handle sandy and abrasive formation fluids. Even paraffin, gyp, and scale won't stop a Moino. Because of the inherent low-velocity movement through the pump, a downhole progressing cavity pump won't emulsify formation fluids. One standard pump handles a wide range of well conditions. The pump's flow rate can easily be adjusted to match these conditions. The rugged, compact drive head saves space, power, and money. With its low profile, it can easily be protected and poses no safety hazard to people or livestock. A Moino downhole pump is inexpensive in initial purchase, installation, and operation. Quick, convenient installation helps minimize the cost of new installations and workovers. All these advantages are made possible by the simple yet ingenious progressing cavity design. The basic pump design consists of one moving element, a single helical steel rotor, and a stationary element, the double-threaded helical elastomeric stator. When the rotor is placed inside the stator, a series of sealed cavities is formed. As the rotor turns, the cavities progress from the bottom of the stator to the top. The effect is similar to a rod pump that is continually on the upstroke. Because the design of a progressing cavity pump is so simple, there are only two basic variables to consider in matching a Moino downhole pump to well conditions. The first variable is capacity. Capacity is determined by the size of the cavities formed between the rotor and stator. Larger cavities produce higher flow rates at a given well depth and rotation speed. The second variable is depth capability, which is determined by the number of seal lines. Seal lines affect the length of the rotor and stator. When equipped with a longer rotor and stator, a Moino downhole pump will pump deeper and at higher pressures at a given capacity rating. Moino manufactures a full line of rugged, high-quality pumping elements and drive heads to match a wide range of production rates. A complete overview of the Moino downhole pump product line will be presented by your program moderator. Moino supplies you with all the technical information you'll need to select the right downhole pump for specific well conditions. The Moino downhole pump technical manual guides you through pump sizing step by step. First, determine the pumping depth desired, the actual gross production rate of the well, the API gravity and abrasive characteristics of the fluid being pumped, and flow line pressure. Begin the selection process by finding on the quick selection guide the depth and capacity for your application. The quick selection guide will give the pump size and speed, the horsepower required, plus drive head and rod size. This is a general selection based upon water at 70 degrees Fahrenheit and 100 psi flow line pressure. Turn to the pump specification sheet for the pump size given on the quick selection guide. Located here are the rotor and stator dimensions, materials of construction, speed guidelines, and drive head and rod selection. Also provided are key installation and accessory item recommendations. The performance data for each pump is located on the back of each pump specification sheet. Enter the curve with the desired pumping depth, line pressure, and flow rate to find the speed necessary to produce the desired volume at that depth and pressure. Check the front of the specification sheet for speed guidelines. Make sure the required speed does not exceed the maximum allowed for the abrasive characteristics listed on the front of the pump specification sheet. If the speed exceeds these guidelines, you need a larger capacity pump. If the fluid gravity is lower than 16 degrees API, consult your Moino representative for assistance in pump selection. Selecting the proper drive head and rod size is just as simple as choosing the right pump. Use the chart on the front of the specification sheet under drive head and rod selection. Reference the pump setting depth and predetermined pump speed on the chart. The point where depth and speed intersect determines the proper drive head and rod size. After you have selected a pumping element and drive head, decide what type of mounting you will use. Then use the driver specification guide to determine motor and pump sheave sizes, belt size, and the center distance between shafts. You will also want to check the materials of construction tables to make sure the chemical additives that will be used to treat the well are compatible with Moino materials of construction. Of course, if you're unsure about an application, your Moino downhole pump technical representative is available for help. Let's use an example to see exactly how the selection process works. Let's say we have a pump setting depth of 3,750 feet and a pumping fluid level of 3,500 feet with minimal flow line pressure. The desired rate is 300 barrels of fluid per day, of which 25 barrels are 32 degrees API oil. The producer has not noticed any gas production, nor is he using any treating chemicals. The well has had no past sand problems, but does have light abrasive characteristics. By examining the quick selection guide, we find that an 18 stage 5 and a DH30 can be used to pump 300 barrels per day from 3,500 feet. Turning to the performance data curve on the back of the 18 stage 5 pump specification sheet, enter the curve at 3,500 feet. Use only the pumping fluid level since there is no additional flow line pressure. Move up to the 300 barrels of fluid per day line. The point of intersection is on the solid black 300 RPM capacity curve. It is very important not to overstate the well's production capability when selecting a pump. This often results in over-pumping the well and may damage the well and the pump. It's better to select an initial pump speed that is slower than the speed required for your estimated well production. You can always gradually increase the speed to match actual well production. The moderator will discuss the finer points of optimum pump selection later in this program. After you've determined the speed required, check the speed guidelines on the front of the pump specification sheet. With light abrasion, it is okay to run up to 400 RPM. The viscosity of 32 degree API oil, in this example, does not require special consideration. To figure the horsepower required, turn again to the performance curve. Move up the guide from the 3,500 foot line to the dashed black 300 RPM horsepower line. Then move directly to the right to a running horsepower of 10.4. The starting torque will require a motor horsepower 1 1/2 times the running horsepower. A 15 horsepower electric motor or its equivalent will be sufficient to operate this system. Now to select the drive head and rod size, go to the drive head and rod selection chart on the front of the spec sheet. Use a pump setting depth of 3,750 feet and a speed of 300 RPM to determine the proper drive head size from the chart. On the top of the chart, you will note that 1-inch rods can be used in this range. Because of the weight of the rod string, always size the drive head using the pump setting depth, not the pumping fluid level. The rod selection is based on new grade D rods. Before using a different grade or size, please consult a Moino technical representative. Using a larger rod than recommended could result in a different drive head selection. Next, go to the DH30 driver specification guide. For the sake of this example, let's use the drive mount for B belts and pulleys with an adjustable motor base and select a motor speed of 1140 RPM. On the chart for 1140 RPM motors with B belt pulleys, the shivs required at 300 RPM are a 7-inch motor shiv and a 7.4-inch gear reducer shiv. The center distance between shafts will be 15.6 inches, and the 3 B belts will be size 54. That's all it takes to select the right Moino downhole pump. Your next consideration will be in choosing the appropriate accessory equipment as well as materials of construction. A Moino downhole pump distributor provides top-quality service by offering a complete line of pump accessories. The Moino pump is designed to use almost any prime mover accepted for oil field use. Electric motors, hydraulic motors, gasoline and diesel engines may all be used to power the downhole pump. You'll also need to select prime mover mounting plates, V or B belts, pulleys and bushings, flow detectors, and any other accessories that may be needed. Just to make sure the selection procedures are clear to you, the program moderator will answer questions, help you work some additional pump selection examples, and discuss pump materials of construction, specific accessory options, and pricing. The Moino downhole pump is designed for quick, easy, inexpensive installation. With standard oil field fittings and tools, the complete drive head with prime mover can be installed in less time than a conventional bottom hole pump and pumping unit. The drive head shaft and rotor have standard API threads that connect with standard sucker rods. Rod sizing depends on the depth and application. It is essential to space out the rod string properly. Position the rotor so it completely engages the stator. Begin by carefully tallying the complete tubing string. Include the stator, the tubing, the flow tee, and the hammer union or flange. Add any other required fittings and accessories between the stator and the drive head. Allow for the drive head to thread down on the flow tee, hammer union, or flange. Attach the Moino stator to the first section of tubing. Make sure the stop pin is on the bottom. Run the stator and tubing into the well. All tubing joints must be tightened to API standards. Power tongs are recommended. Next, estimate the number of sucker rods needed in the string, allowing for standard pony rods and box-by-pin subcouplings to space out the rod string. Make sure the proper combination of ponies and subcouplings are at the well site. It is a good practice to take an extra sucker rod and sufficient pony rods and subcouplings. Also, changeover subcouplings may be needed if the rotor or drive shaft pin dimensions differ from the rod string. Now, with the stator and tubing placed in the well, run the rotor and rod string into the tubing. Use care by slowing down as you run the last few full-length sucker rods. Continue slowly until you encounter resistance indicating the rotor is engaging the stator. As the rotor enters the stator, the rod string may rotate slightly. Ease the rotor into the stator until it touches the stop pin at the bottom. Pull the rod string up so the rotor just comes off the pin. Mark the rod. Be sure the rods are in tension. Pull up 1 to 2 feet. The rod may turn in the opposite direction, indicating that the rotor is properly inserted. Lower the string to the stop pin again. Repeat this procedure several times until you are sure the rotor is completely in the stator. With the rotor on the stop pin, pull up to check your first mark. Repeat the spacing if necessary. Then use the tables in your installation, operation, and maintenance manual to calculate the hydraulic and mechanical rod stretch that will occur after pump-up. To calculate hydraulic rod stretch, use the formula listed in the manual. Let's use an example. Let's say you have a number 4 element with a 7/8" rod 3,500 feet long, and you're pumping fluid with a specific gravity of 1 at 3,000 feet from the surface with 50 pounds flow line pressure. First, refer to the table and locate the constant. Since our example uses a number 4 element with a rod size of 7/8", the constant is 0.350. Enter this constant into the formula along with the depth, flow line pressure, length of rod, and specific gravity of the fluid being pumped. In this example, the hydraulic rod stretch is 3.8 inches. Next, determine the mechanical rod stretch by referring to the chart in the IOM manual and locating the length of your rod. In our example, 3,500 feet of rod will have a mechanical stretch of 7.5 inches. Add the mechanical and hydraulic rod stretch figures together, then add 8 inches. 8 inches is a constant that is always added to the mechanical and hydraulic rod stretch total. When spacing the number 6 element, however, always use 16 as the constant. This constant value will ensure that the rotor will be spaced the necessary distance from the stop pin. In this example, the proper figure to use in order to space out the pump is 19 inches. To continue this installation, measure 19 inches down from the first mark you made on the rod and mark the rod again. Now, pull the rod string up, remove the top rod, and measure the distance from the bottom of the rod to your second mark. Select the ponies and box-by-pin subcouplings that will be equal to this measurement. This will place the rotor the proper distance from the stop pin after pump-up. Of course, you will also want to allow for any other fittings that will be added below the drive head. Do not space out so high that the rotor is prevented from fully engaging the stator after pump-up, but be sure the rotor is spaced far enough off the stop pin to allow for rod stretch after pump-up. Install all pony rods required for spacing below the first full-length sucker rod. Using a short pony and a standard rod elevator, raise the drive head over the well. Carefully lower the drive head into position and fasten it to the top of the rod string. Lower the assembled head and rod string onto the hammer union or flange and then tighten. Before you put the belts on the shivs, confirm as you look down the well that your power source will turn the rod string clockwise. Proper rotational direction is noted on the drive head. Now, with the prime mover installed, the Moino pump is ready for years of trouble-free service. Moino's step-by-step instructions help make the installation run smoothly. Just to make sure these procedures are clear to you, the moderator will answer questions and help you work additional examples. A Moino downhole pump is easy to operate and maintain. Before you start the pump, Recheck all adjustments, alignments, the prime mover mounting, and rod rotation. Be sure the prime mover is correctly wired to the power source. Check the bearing and packing lubrication and the tightness of the backstop brake tension bolt. Always install the safety guards over rotating parts before startup. Activate the prime mover to start the pump. There will be a time lapse before the well pumps up and fluid reaches the surface. The lapse varies depending on the fluid level of the well and the pumping rate. The pump-up curve in your IOM manual will help you estimate the required time. You may want to load the tubing. It is very important to match speed to well conditions. Running the pump too fast for the production rate of the well will pump off all available fluid, and extended operations without fluid will damage the stator. If the well is expected to produce 35 barrels, start the pump at about 30 barrels. Check the fluid level. If it has increased, gradually speed up the pump to match well conditions. Pump-off switches are recommended to avoid running the pump dry. Generally, it is a better production technique to avoid on-off duty. Moino's operating flexibility makes it easy to select a pump or pump speed to match well inflow, even in a stripper well. This may also result in lower energy costs. Remember the effects of abrasion. If the formation fluid has a high sand content, avoid running the pump at the upper half of the published pump speed range. Very high surface transfer pressure and extreme abrasives or low-gravity fluids require special consideration. Your moderator will discuss these special conditions. The Moino downhole pump is designed for minimal maintenance, and it's one of the easiest pumps to work on. Proper lubrication of the packing in the drive head is essential. For best results, packing should be lubricated often with limited quantities of grease. The heavy-duty ball and roller bearings are lubricated at the factory. Under normal conditions, they will not need lubrication for the first month or two of operation. After that time, bearings should be lubricated once a month or about every 800 to 1,000 hours of operation. Packing and bearings use the same type of lubricants. Any EP lithium grease is satisfactory. Do not use sodium or calcium-based grease. The packing gland will require minor adjustments from time to time. This keeps the packing compressed and properly seated. Packing gland nuts can be easily adjusted. A small amount of weepage is normal and helps dissipate heat from the packing. Since the Moino downhole progressing cavity pump has only one moving part downhole, there is little that can go wrong. But if you think a pump is not performing properly, refer to the troubleshooting guide included in the Moino technical manual. Most common problems can be avoided by following the simple maintenance procedures outlined in the installation, operation, and maintenance manual. Your Moino field technician can also help you solve any problems you encounter. The Moino downhole progressing cavity pump features lower cost, less maintenance, better performance, and longer life than conventional pumps. A Moino will handle just about anything you find in a well: sand, gyp, scale, paraffin, and gaseous fluids. Simply by changing the RPM of the pump, you can adjust the pump for 24-hour duty. You can also change the pumping rate as conditions change without pulling the pump. Moino pumps handle viscous and sandy fluids easily. They never experience gas lock. The surface drive is easier to install than massive pump jacks and generally operates more efficiently in the same application. In the final analysis, the progressing cavity pump simply outperforms conventional pumps. Moino sales application engineering and field service personnel are the best in the industry. Robbins & Myers offers downhole pump customers professional support, from technical and application assistance to emergency order expediting and field service expertise. Downhole pumps are supported by a complete line of spare parts and service kits. It's a team approach. Moino quality, service, and manufacturing expertise coupled with top-flight distributors. Economical, dependable. Moino downhole progressing cavity pumps. We're working together to give oil producers the best equipment in the industry. The moderator is now available to answer questions on the Moino downhole pump product line or any information provided in this presentation.